Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to dive into an important set of topics in chemistry, and those topics are gas stoichiometry, kinetic molecular theory, real gas behavior, and deviations from the ideal gas law. These concepts are essential for understanding how gases behave under different conditions, and they play a key role in many areas of chemistry. Our first topic will be gas stoichiometry, and we're going to start with a quick review on some fundamental ideas about gases. Unlike solids and liquids, gases expand to fill any container they occupy, and their particles are in constant motion, colliding with one another and colliding with the walls of their container. This movement is what defines gas behavior, and it's why gases respond so dramatically to changes in pressure, temperature, and volume. To make sense of these relationships, chemists use gas laws, which describe how gases behave under different conditions. We covered these gas laws in the previous special topics lecture. Now, one of the most important reference points in gas behavior is standard temperature and pressure, or STP for short. STP is defined as a temperature of 273 Kelvin, or 0 degrees Celsius, and a pressure of 1 atmosphere. Under these conditions, 1 mole of any ideal gas occupies a volume of 22.4 liters. This makes STP a useful benchmark because it allows us to easily relate the amount of gas to its volume. However, many chemical reaction scenarios do not occur at STP, meaning we need a more general way to analyze gas behaviors under any conditions. And this is where the ideal gas law becomes essential. The ideal gas law is a powerful equation that allows us to determine how gases behave when they're not at STP. And it's written as PV equals nRT. P is pressure, V is volume, N is the number of moles of gas, R is the ideal gas constant, and T is the temperature in Kelvin. Like we mentioned in the previous lecture where we first introduced this equation, it's incredibly useful because it allows us to solve for any of these variables as long as we know the others. And it also combines the relationships described in simpler gas laws like Boyle's law and Charles' law into a single, more comprehensive equation. Now, the best way to solidify our understanding of these concepts is to apply them in practice problems. Specifically, we need to know 2 key cases for this general chemistry class. The first one is using STP conditions to determine gas volume or moles. The second case is using the ideal gas law when conditions are not at STP. So let's go get started with this first one. This first problem says 92 grams of ethanol, which has a molecular weight of 46 grams per mole, reacts to completion with 96 grams of oxygen at STP following the balanced reaction below. What is the volume of the system after the reaction? So in this reaction, we have 92 grams of ethanol and 96 grams of oxygen gas. Our goal is to determine the total volume of gas. To start, we want to convert the given masses into moles, and we can do that using their molar masses. For ethanol, we have 92 grams, and the molar mass of ethanol is 46 grams per mole. So we'll put 46 grams in the denominator and 1 mole in the numerator because we want grams to cancel out, and we want our final answer to have units of moles of ethanol. When we calculate this, we get 2 moles of ethanol. Then we want to do the same for oxygen gas. The molar mass for oxygen gas is 32 grams per mole. When we calculate this, we get 3 moles of oxygen gas. It was important for us to convert these given masses to moles because this will help us figure out the limiting reactant. That is the reactant that gets used up first as the reaction goes to completion. Here, we also need to rely on the balanced equation we're given. From the balanced equation, we see that 1 mole of ethanol reacts with 3 moles of oxygen gas, and that produces 2 moles of carbon dioxide and 3 moles of water. Now, what we have to start off with is 2 moles of ethanol and 3 moles of oxygen gas. So with just 1 mole of ethanol, we're going to need 3 moles of oxygen gas so that the reaction can produce 2 moles of carbon dioxide and 3 moles of water. Now, from this, we've already used up all the oxygen gas we have. We are left with 1 mole of ethanol. This means that oxygen gas is the limiting reactant and ethanol is the excess reactant. So we have produced 2 moles of carbon dioxide and 3 moles of water. That's a total of 5 moles of gas as product. But we also have that 1 mole of ethanol that remains. We want to account for that and state that the total moles of gas that is present after the reaction goes to completion is 6 moles of gas. And we are trying to determine the total volume of these 6 moles of gas. The problem tells us we're operating under STP, which means we can calculate this very easily. Under STP, 1 mole of any ideal gas occupies 22.4 liters. Since we have 6 moles of gas, we want to multiply this value by 6, and that gets us 134.4 liters. This is our final answer. Now we can move into our second problem. Our second problem reads, hydrogen peroxide undergoes photolysis to produce water and oxygen gas according to the balanced equation. If 340 grams of hydrogen peroxide is allowed to fully decompose in a closed 4-liter container at 27 degrees Celsius, find the appropriate final pressure exerted by the oxygen gas. In this problem, we want to start again by converting mass to moles. The molar mass of hydrogen peroxide is equal to 34 grams per mole. And we know we're starting off with 340 grams of hydrogen peroxide. So we'll multiply this by 1 mole in the numerator, 34 grams in the denominator, so grams cancel out, and we get our final answer in units of moles of hydrogen peroxide. When we calculate this, we'll get 10. Now that we know that, we're going to use the mole ratios in our balanced reaction to determine the amount of oxygen gas we can actually produce from 10 moles of hydrogen peroxide. We notice from the balanced reaction, it takes 2 moles of hydrogen peroxide to produce just 1 mole of oxygen gas. So with 10 moles of hydrogen peroxide, we can produce 5 moles of oxygen gas. Now we can use our ideal gas law to solve for the final pressure. We use the ideal gas law here because this is not under STP conditions, so we can't just say the pressure is 1 atmosphere and call it a day. Instead, we have to use our ideal gas law. Our ideal gas law is PV equals nRT. Since we're solving for pressure, we can isolate the variable. P is equal to nRT divided by V. We know the number of moles of oxygen gas that's produced, N is equal to 5. R is our gas constant. T is temperature. Now here we're given the temperature in 27 degrees Celsius in units of Celsius. We want to convert that to Kelvin. You always want to have your temperature in units of Kelvin. So to do that, we simply add 273 to 27, and that gets us 300 Kelvin. So this is our temperature. For volume, it's going to be 4 liters. So we have everything we need to plug this into our equation. Pressure is equal to 10 moles. R is equal to 0.08206 liters times atmosphere divided by moles times Kelvin. And then we multiply this with temperature, which is 300 Kelvin. This will all be divided by the volume, which is 4 liters. Notice that liters cancel out, moles cancel out, and Kelvin cancel out. What we're left with is atmospheres, which is the exact unit we want if we're calculating pressure. Plug this into a calculator and you're going to get 30.8 atmosphere. So the final pressure is 30.8 atmosphere. Now that we've explored gas stoichiometry and we learned how to apply gas laws to real-world problems, it's time to take a step back and ask a deeper question. Why do gases behave the way they do? We've seen that gases expand to fill their containers, that their volume, pressure, and temperature are all interrelated, and that their behavior can be described mathematically. But to truly understand gases, we need to go beyond the equations and look at what's happening on a molecular level. This brings us to the kinetic molecular theory, or KMT for short. KMT helps explain the macroscopic properties of gases, so things like pressure, temperature, and volume, by looking at the microscopic behavior of individual gas particles. In other words, instead of just using equations to describe gases, KMT tells us why those equations work. So at its core, the kinetic molecular theory is based on a few key assumptions about gas particles. The first assumption is that gas particles are simple, hard spheres. In other words, we assume that individual gas molecules are tiny, round particles with no internal structure, and this simplifies how we model their motions and interactions. The second assumption is that gas particles have no volume compared to the size of their container. Although real gas molecules do have some volume, KMT assumes that they are so small that we can ignore it. This is what allows gases to be compressed much more than solids or liquids. Third, gas particles experience completely elastic collisions. This means that when gas molecules collide with each other or collide with the walls of their container, they don't just lose energy. They simply bounce off each other like billiard balls. There are no intermolecular forces in an ideal gas, meaning the particles don't attract or repel each other. The fourth assumption is that the average kinetic energy of gas particles, that's directly proportional to temperature. This is one of the most important ideas in KMT. As temperature increases, then the kinetic energy also increases. This is why heating a gas causes its molecules to move faster, and why higher temperatures result in higher pressures and larger volumes. So this relationship is given by the equation you see here. Ke, that's kinetic energy, It's equal to 1/2 multiplied by just K. This is Boltzmann's constant. And then that's multiplied by temperature. Finally, kinetic energy is also related to mass and velocity. So the kinetic energy of a particle, that's given by this equation. Kinetic energy is equal to 1/2 mv squared, where m is mass, v is velocity. This tells us that for gases at the same temperature, lighter molecules move faster than heavier ones. So for example, helium atoms are going to move much faster than oxygen molecules at the same temperature because helium has a much lower mass. These principles, they help us explain why ideal gases behave as they do. Pressure arises from gas molecules colliding with the walls of their container. Temperature reflects the average kinetic energy of the molecules. And because gas molecules are always moving and colliding, their velocities are distributed over a range of values. This is actually described by something called the Maxwell-Boltzmann Distribution. We're going to get into that in a second. For now, the key takeaway is that the kinetic molecular theory gives us a microscopic explanation for the behavior of gases. Now what we need to do is take a closer look at how gas molecules actually move. Up until now, we've been talking about gases in general terms, saying that temperature is related to kinetic energy and that gases are always in motion. But in reality, not all gas molecules move at the same speed. Even in a gas sample at a single fixed temperature, there's a range of molecular speeds. Some molecules move faster, some move slower, and most fall somewhere in between. And that brings us to the Maxwell-Boltzmann distribution, which describes the spread of speeds among gas molecules in a sample. Instead of all molecules moving at one uniform speed, they exhibit a distribution due to molecular collisions and energy exchanges. Some particles gain energy and speed up, while others lose energy and slow down, and that creates a characteristic curve that represents the probability of finding a molecule moving at a certain velocity. To fully understand this concept, let's first revisit the relationship between energy, mass, and velocity, and then I'm going to show you some curves and we'll talk about it. We know that kinetic energy of a gas molecule, it can be expressed one of two different ways. We can say that kinetic energy is equal to 1/2 mv squared, where m is mass and v is velocity. Kinetic energy is also equal to 1/2 kT, where k is Boltzmann's constant and t is temperature. Since they are both definitions of kinetic energy, we can actually set them equal to each other. And by setting these equations equal to each other, we get the following equation. mv squared is equal to kT. This equation tells us something important. At a constant temperature, the velocity of a gas molecule depends on its mass. The heavier the molecule, the lower its velocity. And the lighter the molecule, the faster it moves. Now let's look at two key cases that describe how gas molecules distribute their speeds under different conditions. The first case is how temperature affects speed. If we take a sample of the same gas and we increase the temperature, what happens to the speed of the molecules? At a higher temperature, the gas molecules gain kinetic energy and they move faster. This means that the distribution of speeds spreads out with more molecules moving at a higher velocity. So this is how the curve for that high temperature is going to look like. The distribution of those speeds is in the higher range. At a lower temperature, the molecules move slower. So the distribution becomes narrower and it shifts it towards lower speeds. So this is the distribution for the velocities at a low temperature. Notice it's in a smaller range for velocities and the curve is also narrow. So visually we can see this in the Maxwell-Boltzmann distribution curves in the figure. At a low temperature, let me repeat, at a low temperature, all right, the gas has a steep, narrow peak that describes the distribution of speeds. So a low temperature gas has a steep, narrow peak, meaning most molecules are clustered around a low speed. At higher temperatures, a higher temperature gas, it has a broader, flatter curve, meaning a wider range of molecular speeds with more molecules reaching higher speeds, higher velocities. Now, the second case we want to consider is how mass affects speed. Now, what happens if we compare different gases at the same temperature? Since temperature is directly related to kinetic energy, two different gases at the same temperature will have the same average kinetic energy. However, because kinetic energy depends on both mass and velocity, lighter gases must move faster to maintain the same energy as heavier gases. So that means looking at the distribution here, lighter gas molecules like hydrogen or helium, they move faster. So their Maxwell-Boltzmann distribution is broader and it's shifted towards higher speeds. Heavier gas molecules like oxygen or xenon, they move slower in comparison to hydrogen or helium, meaning their distribution is narrower and it's shifted towards lower speeds or velocities. So in summary, the takeaways here is that higher temperature results in faster molecular speeds and a broader distribution, and higher molecular mass results in slower molecular speeds and a narrower distribution. The Maxwell-Boltzmann distribution help us visualize the range of speeds in a gas sample, and it explains why some molecules move much faster than others, even if the gas is at a uniform speed, at a uniform temperature. So please be familiar with these two cases and the information we can extract from their relative Maxwell-Boltzmann distributions. Now that we understand how gas molecules move and how their speeds are distributed, we can apply this knowledge to two important processes: diffusion and effusion. These concepts describe how gases spread and move through different environments, and they're directly related to the Maxwell-Boltzmann distribution we just covered. Diffusion is the spontaneous spreading of one substance through another. This happens when gas molecules move from an area of high concentration to an area of low concentration. A simple example of diffusion is when you spray perfume in one corner of a room, and after a short time, you can smell it throughout the whole room. And this occurs because the gas molecules are constantly moving and colliding and gradually spreading out in all directions. Effusion, on the other hand, describes the movement of gas particles through a small hole or narrow opening without collisions between molecules. So unlike diffusion, which involves molecules interacting with each other as they spread, effusion occurs when individual gas molecules pass through a tiny hole in a barrier without bouncing off of one another. And this can be observed in a vacuum chamber where a gas slowly escapes through a small pinhole without external forces pushing it out. Since both diffusion and effusion involve the movement of gas molecules, their rates depend on molecular speed, which we know is influenced by temperature and molar mass. This brings us to an important law called Graham's Law of Effusion. This law helps us compare the rates of diffusion and effusion for different gases. And to understand this, we want to go back to the kinetic energy equations we discussed earlier, where we said kinetic energy is equal to 1/2 mv squared, and that's equal to 1/2 kT. Since temperature is the same for both gases in our comparison here, their average kinetic energies are also the same. This means that lighter molecules must move faster to have the same kinetic energy as heavier molecules. So then, using this idea, Graham's law states that the ratio of diffusion or the ratio of effusion rates for two gases, that's going to be inversely proportional to the square root of their molar masses. And mathematically, that's expressed in this equation you see here. V1 divided by V2 is equal to the square root of molar mass 2 divided by molar mass 1. So here, V1 and V2 are either the diffusion or effusion rates of the two gases, and MM1 and MM2 are their respective molar masses. This equation tells us that lighter gases diffuse and effuse faster than heavier gases. For example, helium, a very light gas, will diffuse much faster than oxygen or nitrogen. So in summary here, diffusion occurs when gases mix and spread due to molecular motion. Effusion occurs when gas molecules pass through a small hole without collisions. Graham's law allows us to compare how quickly different gases diffuse or effuse based on their molar masses. And from that, we know lighter gases move faster, which means they diffuse and effuse more rapidly than heavier gases. Now let's take a moment or two to tackle a couple of practice problems. This first one says, at a temperature of 300 Kelvin, all gases like helium, argon, so on, have blank average kinetic energy, and they have blank. Our answer choices are different and the same diffusion rates, different and different average velocities, the same and the same diffusion rates, or the same and different average velocities. In order to answer this problem, we need to take advantage of both equations for kinetic energy. Looking at this first equation, it tells us that kinetic energy only depends on temperature, not on the type of gas. So since all the gases in this problem are at the same temperature, 300 Kelvin, they must all have the same average kinetic energy. But even though different gases have the same kinetic energy, their individual molecular velocities, those can be different. And we can use this equation to understand that relationship. This equation tells us that velocity depends on the mass of the molecule. Lighter gases move faster, while heavier gases move slower. And if we were going to order these three, helium is the lightest gas, so it's going to have the fastest molecular velocity. And krypton is going to be the heaviest of the three, so it's going to have the slowest velocity. Argon is going to fall somewhere in between. So for this problem, at a temperature of 300 Kelvin, all gases are going to have the same average kinetic energy, but they're going to have different average velocities. So the correct answer here is D. This next problem says, what is the ratio of effusion of iodine gas to nitrogen gas at the same temperature. For this problem, we're going to use Graham's law, which states that the ratio of effusion rates for two gases is given by this equation. V1 divided by V2 is equal to the molar mass of gas 2 divided by the molar mass of gas 1. Now we can get the molar mass of iodine gas and nitrogen gas from the periodic table. So for nitrogen, one nitrogen atom is 14 grams per mole. If there's two nitrogens for N2, this is going to be 28 grams per mole. That's the molar mass of nitrogen gas. And we do the same for iodine gas. This is going to be 254 grams per mole. Now let's go ahead and plug these into the equation. V1 divided by V2, that's equal to V iodine gas to V nitrogen gas. And that's going to be equal to the molar mass of gas 2, which is nitrogen, so 28 grams per mole, divided by the molar mass of gas 1, which is iodine gas. That's 254 grams per mole. Our units cancel out, and we're going to get a ratio of the effusion of iodine gas to nitrogen gas. When we plug this into the calculator, we're going to get 0.33, or this is also equal to 1/3. This means that iodine gas effuses at about 1/3 the rate of the nitrogen gas. So 1/3 of the rate of nitrogen gas. That means there's a 1-to-3 ratio between iodine gas and nitrogen gas. The correct answer here is A. Now, up to this point, we've treated gases as ideal. So we worked through all of these concepts under the assumption that we are treating gases as ideal and they follow the ideal gas law perfectly. However, in the real world, no gas is truly ideal. While many gases behave close to ideal under normal conditions, there are situations where they deviate from this behavior, especially under high pressure and low temperature. So let's talk about this a little more. The ideal gas law, it assumes that gas particles have no volume. They're treated as infinitely small points. In addition, it assumes that gas particles do not interact. There are no attractive or repulsive forces between them. But in reality, these assumptions are not entirely true. Real gases do occupy space. Gas molecules are not infinitely small, they take up some volume. In addition, they do interact with each other. Under certain conditions, gas molecules experience attractive or repulsive forces which affect their behavior. Now, there are two major factors that cause real gases to deviate from the ideal gas law. The first one is deviations due to pressure. At very high pressure, gas molecules are forced close together, and their individual volumes become significant. The space they occupy cannot be ignored, meaning the assumption that gases have no volume, that breaks down. In an ideal gas, we assume that most of the volume is just empty space, but at high pressure, gas molecules take up a larger fraction of the total space, leading to lower than expected volumes when applying the ideal gas law. The other deviation is deviations due to temperature. At very low temperatures, gas molecules move slowly, which allows them to experience weak attractive forces with one another. This means that instead of moving freely as ideal gases do, some molecules stick together slightly, reducing the overall pressure that they exert on the container. But in an ideal gas, we assume particles do not attract or repel each other. So in real gases, it's important to note that these weak forces, they become noticeable at those low temperatures. So to correct for these non-ideal behaviors, we need a more advanced equation than the ideal gas law. And this brings us to the van der Waals equation. The van der Waals equation is a modified version of the ideal gas law that accounts for the volume of gas molecules and the attractive forces between them. So this equation includes two correction factors: the A term, which corrects for the attractive forces between gas molecules, and the B term, which corrects for the finite volume of the molecules themselves. If a gas were truly ideal, A and B would both be zero, and it would reduce the equation back to PV equals nRT. But for real gases, the larger these terms are, the less ideal the gas behaves. Now, some gases behave more ideally than others, and we can rank them based on how strongly they deviate from ideal behavior using the A and B correction factors in the van der Waals equation. So generally speaking, gases that tend to behave more ideally, these are gases that are small in size, and they are nonpolar, and they do not attract or repel each other. Some great examples of ideal-like gases include helium and hydrogen gas. Helium atoms are very small and they don't stick together at all, making them nearly ideal. And then hydrogen molecules, they're also small and they're nonpolar, meaning they have minimal attractive forces. Gases that deviate more from ideal behavior, they tend to be larger in size, or they have noticeable attractions between molecules, meaning they do not move completely independently. Some examples are water, ammonia, sulfur hexafluoride, and carbon tetrachloride. So water molecules, for example, they're not just small spheres. They can actually attract each other through intermolecular forces, and that makes them deviate from ideality. Ammonia, similar to water, ammonia molecules attract each other. That leads to deviations. Then for sulfur hexafluoride and carbon tetrachloride, these molecules are much larger than hydrogen or helium, so their volumes cannot be ignored. Now, we haven't learned about intermolecular forces yet. That's going to be our next lesson. But a simple way to think about this right now is that gases that behave ideally are small and independent. They move freely without getting in each other's way. Gases that deviate from ideal behavior are either larger, so they take up noticeable space, or they're sticky, so they slightly cling to each other, and that reduces their movement. So when we're comparing gases, helium, it's nearly perfect. It's tiny and it doesn't stick to anything. And water vapor, that's going to be farther from ideal behavior. It's larger and it has a tendency to pull molecules together. In the next lecture, I want to repeat, we will talk about intermolecular forces, and this will make more sense. But for now, this simplification will do. So our summary for this section is ideal gases follow the ideal gas law, PV equals nRT. But real gases, they don't always behave this way. Real gases deviate due to high pressure. This is where molecular volume cannot be ignored, and low temperature, where molecules begin to attract each other. The van der Waals equation, it corrects for real gas behavior by adding terms that account for attraction, A, and molecular volume, B. Helium and hydrogen are the most ideal gases, while larger gases or gases that slightly attract each other behave less ideally. Keeping that in mind, let's tackle a couple of practice problems. This first question asks, which of the following conditions would cause a gas to behave less ideally? The answered choices are low pressure, high pressure, large container volume, or high temperature. We know that gases, they behave most ideally under conditions where the ideal gas law assumptions hold up well. That means low pressure, because low pressures keep gas molecules far apart, making their own volume negligible. That also means high temperatures because they ensure that gas molecules move quickly and they don't have time to interact with each other. And it also means a larger container volume because that gives molecules plenty of space, reducing the chance of intermolecular interactions. However, gases deviate from ideal behavior under conditions where these assumptions start to break down. So high pressures because they force molecules closer together, making molecular volume significant and causing interactions. And also low temperatures because they slow molecules down, making attractive forces more noticeable. Since we're asked which condition makes a gas behave less ideally, we want to select high pressure. Again, high pressures force molecules closer together, making molecular volume significant and causing interactions, and that causes gases to deviate from ideal behavior. The second question says rank the following gases from most ideal to least ideal based on the A term in the van der Waals equation. The A term in the van der Waals equation accounts for attractive forces between gas molecules. The larger the A term, the stronger the attraction between molecules, meaning the gas behaves less ideally. To rank the gases, we need to consider that larger molecules tend to have stronger attractions because they have more electrons, leading to stronger forces. And also more reactive molecules tend to interact more strongly with each other. So now let's compare the gases. We have nitrogen gas, fluorine, and then sulfur hexafluoride. Nitrogen is going to be the smallest of the three. It's small, it's nonpolar, it's going to have weak attractions. It is going to be the most ideal because it's going to have a small A term. Fluorine here, this is also nonpolar, but it's slightly bigger than nitrogen gas, so it's a little bit more reactive, meaning its molecules attract each other slightly more. So it's going to be less ideal than nitrogen gas, but still not extreme. You can even say almost approximately within the sphere of each other in terms of how they deviate from ideal behavior. Finally, we have sulfur hexafluoride. This is much larger than nitrogen gas and fluorine gas. It has a larger electron cloud, meaning stronger attractions. So it's going to be the least ideal. So it's going to have the highest A value. So we can write nitrogen gas is going to be the most ideal, followed by approximately the fluorine gas, and then the sulfur hexafluoride. This is going to be the least ideal. And with that, we've completed this lecture. I hope that this has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.